before I start for the first 10 minutes of blank. Okay, so start again. We're going to look at algebraic integers. So we're working over complex numbers. So everything we deal with is a complex number at this point. An algebraic number is a zero of a polynomial with integer coefficients. So 2x squared minus 3. The zeros of that are root 3 on 2 and minus root 3 on 2. They're algebraic numbers. An algebraic integer is a zero of a monic polynomial with integer coefficients. So the zeros of x squared minus 3 are plus or minus root 3. They're algebraic integers. So algebraic integers are a special case of algebraic numbers. And in fact, the relation between algebraic integers and algebraic numbers is essentially the same as the relation between the integers and rationals. So the jargon is that the algebraic numbers are the field of fractions of the ring of algebraic integers, and the rationals are the field of fractions of integers. But we don't need to know that, so don't worry too much. Now, we need to be a little bit careful. You can't always tell by staring at the expression for a number whether it's an algebraic integer or not. So you look at root 2, it's root of t squared minus 2, fine. But 1 plus root 5 on 2 is also an algebraic integer. Now, 1/2 is not an algebraic integer. We'll see that rational numbers. The rational number is an algebraic integer is an integer, but the point is you can write down a polynomial. I think it's like t squared minus t plus 1, which will have these as roots. Okay, and so as I said, you can't. Now, in fact, there is a characterization of when the quadratic case of when you get an algebraic integer. But just my point simply is that you can't always tell by staring at the number if it's an algebraic integer or not. You can see that this is an algebraic number, and I'm telling you it's an algebraic integer because you can write down a monic polynomial with integer coefficients that it satisfies. Now, we can make some progress without too much effort because clearly the eigenvalues of the adjacency matrix of a graph are algebraic integers because they're the zeros of the characteristic polynomial. Okay, and so each eigenvalue satisfies a monic polynomial with integer coefficients, so they're algebraic integers. So eigenvalues of graphs are algebraic integers, which is why they're relevant to us. Now the interesting point is that the converse is true. Every algebraic integer is an eigenvalue of an integer matrix. Okay. Now to prove that, you've got to construct the matrix, and the reason, let's put some color on this. The magic matrix you want is called the companion matrix. Now, these are discussed in the algebra notes in one of the earlier chapters. But if you're given a monic polynomial with, in this case, degree d coefficients, or p0 is 1 because it's monic, p1 through pd just integers, then the companion matrix is you write down the entries, the coefficients in reverse order with a minus sign, and then you put a d by d identity, or d minus 1 by d minus 1 identity here. So you get a matrix of this form. So 0 minus p. So it looks like that. So there's a big identity submatrix in there. I'm just pointing out that the determinant of this matrix will be PD up to sign, and the trace will be this term, again up to sign. Okay, so but that's not too important. So the point is you can write down this companion matrix, and it's a straightforward exercise to prove that if the characteristic polynomial of the companion matrix is exactly the polynomial you started with. Now, I suggest you prove it for, sit down and convince yourself for polynomial of degree 3 and leave it at that, because there's no difference in the general thing. But it's easy to prove. So this is the companion matrix, and they're quite important and useful, and in particular because of this connection. So the point then is that the companion matrix of an integer polynomial is an integer matrix. And so its eigenvalues are algebraic integers. And so we have that a number is an algebraic integer if and only if it's a 0, if and only if it's an eigenvalue of an integer matrix. Okay, now we'll use that in a minute. It's an algebraic number. The same argument shows you if it's an algebraic number, then it's the 0 of a rational matrix, an eigenvalue of a rational matrix. Now, if you have a rational matrix, there's an integer m such that m times that matrix is an integer matrix. Okay, and so that tells you a useful fact that if for every algebraic number alpha, there's an integer m such that m times alpha is an algebraic integer. Okay, and that's just playing with the matrices because we convert any rational matrix to an integer matrix, and the eigenvalues of an integer matrix are algebraic integers. Okay, so the point is we can use number theory. The number theorists, of course, don't normally use this. They'll probably express things in terms of modules and things. But since we've done the dirty work with matrices, it's useful. So this is what I was just saying. Now, the next thing we need to know is that the algebraic integers form a ring. So the simplest way to state, or a simple way to state this is to say that the algebraic integers is closed on multiplication and closed on the difference. Okay. Now, to get the difference, we observe that if we have integer matrices A and B, then this matrix is an integer matrix. And from what we know about Kronecker products, the eigenvalues of this matrix are the difference eigenvalue of A minus eigenvalue of B. And so that tells you that those differences are algebraic integers. And so the difference of two algebraic integers is an algebraic integer. Now, to get the products, you just use the Kronecker product, A times B. The eigenvalues out of the products, eigenvalue of A times eigenvalue of B. Since A Kronecker B is an integer matrix, its eigenvalues are algebraic integers. So we get a very, given the basic facts about Kronecker product, we get very simple proofs of an important fact that the algebraic integers form a ring. They close under multiplication, addition, and multiplication by minus 1. Any questions at this point? And so the conclusion of that is I just said that the algebraic integers form a ring and the algebraic numbers form a field. And you can think about that for a second. The only thing that you actually need for the second claim is to notice that the inverse of rational matrix is rational. And so that tells you if alpha is an algebraic number, then 1 over alpha is an algebraic number. And then this is repeating something I said before, but now if you've seen fields of fractions or constructed things, the rationals from the reals, then this will make sense. If you haven't, you can just ignore it. Now, the next fact I'm going to is I don't have a simple proof using matrices, and it's fairly important. If the entries of a square matrix A are algebraic integers, its eigenvalues are algebraic integers. So you can't get more algebraic integers by sort of taking matrices with algebraic integers as entries. So the tower stops immediately. So this isn't too hard to prove, but yeah, I'm not a number theorist. I'm happy just to use some of the basic results. And so this is a result which we'll get to use occasionally. Well, we use occasionally in working on quantum walks. We might need it once or twice here. So if the entries are square matrix are algebraic integers, its eigenvalues are algebraic integers. So in other words, if you have a monic polynomial whose coefficients are algebraic integers, then the zeros are algebraic integers. And so this is the basic fact that's related to something called normal closure. I'll try to write that down. Something called and it isn't spectacularly difficult to prove, but I don't want to spend the time on it when I don't need to. So now we need a bit more theory about dealing with algebraic integers. So we're assuming now I've got an algebraic integer alpha. So it's otherwise a monic integer polynomial degree D for argument's sake. Now, if f and g are polynomials with alpha as a root, then alpha is also a root of their GCD, and their GCD is monic. So if you've got an algebraic number, there's a unique monic polynomial of least degree, which it satisfies. So it satisfies lots of polynomials, but there's there's a unique monic polynomial of least degree, and it's just this GCD argument that you need to prove that. And so we call that the minimal polynomial of alpha. This is literally the same proof as when you prove there's unique minimal polynomial of the matrix. So it's a monic polynomial of least degree, and you use the GCD argument, so it's essentially the same proof. Now, the other comment which is worth noting is that this polynomial H would be irreducible, because if it factors over the integers into two polynomials, then alpha must be a root of one of those two factors, and so H didn't have minimal degree. There's also a non-trivial result here that if you have a polynomial, integer polynomial which factors over the rationals and it factors over the integers, that's due to Gauss. But I'm trying not to do too much number theory. Now the other comment which is fairly important for us is that if an algebraic integer is rational, not just for us, but in other contexts too, if an algebraic integer is rational, then it's actually an integer. And here I'm following well, this is a bit messy, so let me rewrite it as I go. So suppose, let's just look at an example. Suppose we have tau cubed plus a tau squared plus b tau plus c. This is going to be essentially the same as the proof that the square root of 2 is irrational. And now let's put tau equals, okay, suppose this is equal to 0. And now set tau equals x on y with x, y in z and x comma y co-prime. Okay, so now, and then all we do is we substitute this into the first expression, and then I'm going to replace tau by x on y, and then multiply by y cubed, and I get x cubed plus a x squared y plus b x y squared plus c y cubed 0. And now let p be a prime that divides y. Well, it must divide this term, and this term, and so it divides this term. And if p divides x cubed, it divides x. So x and y have a common factor. So this is the same, if you've ever seen a proof that root 2 is rational, it's the same argument. Okay, so, and I should reiterate that this is actually an important result, which gets a lot of use. So that if you have an algebra, you'll see it's using it. If you have an algebraic number and it's rational, then it's an integer. Okay, so we'll be using that. And so, okay, so it's a straightforward piece of number theory, but then the next comment is if you have an algebraic integer with minimal polynomial 5t, and this integer alpha is an eigenvalue of an integer matrix, then 5t divides the characteristic polynomial of A. Now that's easy to see because certainly alpha is a 0 of 5at, and it's a 0 of 5t, and so it's a 0 of the GCD. But you've chosen 5t to be the minimal of its degree, so this must actually divide. So you can always factor the characteristic polynomial into products of minimal polynomials, and each of those minimal polynomials is irreducible, no further factors. Now, one consequence of this is an example sort of thing. It follows that the cube root of 2 is not an eigenvalue of a graph. Let me be an optimist and ask, any ideas why? The hint is to think about the minimal polynomial as a cube root of 2. Now, it's obviously t cubed minus 2. Okay, now what are the roots of t cubed minus 2? Well, there are 3 of them. 1 is real and 2 are complex. Now, if cube root of 2 is an eigenvalue of a graph, then the characteristic polynomial is divisible by t cubed minus 2. And so that means along with the cube root of 2, you have 2 complex roots. But the eigenvalues of a graph are real. Okay, so I mean, this is interesting. I mean, we're not going to be worried. There is a question as to which algebraic integers can be eigenvalues of graphs. Once you see this, okay, so not all algebraic integers are eigenvalues of graphs. So which ones are? And so that's an interesting question. And there's a fair bit of work done by some very well-known people. the answer is clearly necessary that if you look at the minimal polynomial of the alpha, that all the zeros be real. So it's a necessary condition for a algebraic integer to be an eigenvalue of a graph. And so if it satisfies that condition, the algebraic integer is called totally real. Okay, and so that's a necessary condition. And well, it was then proved that, and there was more or less a conjecture that that was enough to make something a graph eigenvalue, and that was proved. The nicest result was proved by a guy called Salles, who proved that every totally real algebraic integer is an eigenvalue of a tree. Okay, so anyway, that's not going to affect anything we do from now on. So I've talked about algebraic integers and some of the basic results. The one result which I haven't proved is simply saying that if a matrix has algebraic integers as entries in a square, then its eigenvalues are again algebraic integers. The other things are all reasonably straightforward. And we've defined the minimal polynomial of an algebraic integer. Okay, and you can think of it as an analog to the minimal polynomial of a matrix, although you don't see as much about minimal polynomials as you ought to in your undergraduate courses. The next terminology is two algebraic integers are conjugate if they have the same minimal polynomial. Okay, now conjugate sounds like a group theory term, and in fact, well, it is. If they're conjugate, then there's an automorphism, a field automorphism, which maps one root to the other. Now I'll be quoting one or two results about field automorphisms in a bit, but all I'm saying is that this conjugate definition is, well, it's a reasonable term because it corresponds so that, yeah, okay. So they're conjugate if and only if they're related by a field automorphism. We won't need that explicitly, although I've said it's true. Okay, so we'll leave it at that. Now, do you want to say anything more about that? So sums and products of algebraic integers from a ring. Algebraic integers have a minimal polynomial if the okay, we got, and if the entries are matrix algebraic integers, the eigenvalues are algebraic integers. These are the basic results. I'll need to come back to the field automorphisms. Now, the reason we need this is because I want to work with the eigenvalue support of a vertex or of a state in a graph. Okay, so, and I could have been lazy and just worked with vertex states, but for reasons which I might get to today, I'm going to work with subset states. So technically a subset state is a density that's diagonal and has C diagonal entries equal to 1 on C and all other entries equal 0. So in other words, you take a diagonal matrix with diagonal entries 1 and 0 and then scale it so the trace is 1. Now, for what we're doing, the trace doesn't play any particular role. So sometimes I'll be lazy and just take a 0, 1 diagonal matrix and refer to that as a state, which it isn't because the trace is not equal to 1, but you can always fix it. So that's not a big problem. So the point is, if D is a subset state, then it's given by a subset of the vertices, and then the entries on the diagonal corresponding to the vertices in the subset will be 1 over the size of the subset. And so I'll be denoting this by D over S. And sometimes this will be have trace 1, and sometimes I won't care. So in particular, if I'm ignoring the trace, then any subset state, well, you take a sum of vertex states and then scale. Okay. Now, this is the point with this sort of theory. I mean, you've got to remember, this is all being developed in real time. Okay, and we're trying to extend things. And so the vertex states and pure states where theory works, we can understand what goes on. And so it's natural to try and push things a bit. And so this is a nice class of states which are not pure, but are reasonably simple. The entries are real, so whatever we learned about real states will apply. So it's a nice class of states to work with. There's a more general concept called group state transfer that Bill Martin, one of his students, worked with. But this is the special case that I need. And so in particular, any vertex state is a subset state. Now I've got a new word there, substates, which means subset states are real, and hence we have perfect transfer between subset states at time tau. Both states are periodic at time 2 tau. I will fix that. And both states have the same eigenvalue support. Well, that's true of any transfer. So, so the issue is, well, okay, so they're real, and so if we get transfer from state 1 to state 2 at time tau, we have transfer from state 2 to state 1 at time tau, and at time 2 tau, they're each periodic. Okay, so just like vertex states. And now the easiest way to get periodicity is to choose the Hamiltonian. It's going to be an integer matrix we're going to do today, but choose it so its eigenvalues for integers. Then it's easy to see that U of t itself is periodic. So everything's periodic, all vertices are periodic. We can pack up and go home as far as periodicity is concerned. Okay. In a sense, what we're going to do is prove a converse. We're going to say that if a vertex is periodic, then the eigenvalue support is basically integers. Now, basically, it's one of these words like essentially in mathematics, which is actually a synonym for not. So what do I actually mean? So either it's an integer or it satisfies a monic quadratic polynomial. Now, the algebraic numbers that satisfy the algebraic integers that satisfy monic quadratic polynomials are called quadratic integers. And there's an extensive theory of this. I mean, the number theorists, have worked very hard on that particular problem, or things unrelated to that. So quadratic integers play a big role. And so what's going to happen? We're going to discover if we get periodicity from a continuous walk, then the eigenvalue support the entries consist of quadratic integers. So they don't have to be integers. They might be, but at worst they can be as quadratic. And in fact, a bit more is true. So one consequence of this will be that if you look at the eigenvalue support, any two distinct elements of the eigenvalue support differ by at least one. They can't be too close together. Okay, so that's why these guys will come up. And as I've said several times already, I'm going to be assuming throughout that the Hamiltonian has entries integers. Okay, so I want the eigenvalues to be algebraic integers. Okay, and so assuming that the Hamiltonian is integer is how we do that. Now, we can also say things about when the Hamiltonian, so the Hamiltonian, it's going to be integers, and so the idempotence will be real, okay? And that's something we use the fact the idempotents are real to get periodicity at some points. Okay, so this is, but the point is that the Hamiltonian could be the adjacency matrix, or the Laplacian, or the signless Laplacian, or various other weightings, so long as the entries are integers. Okay, now for I'm doing this for subset states. In the notes, it's all worked out for vertex states. Okay, but the same thing applies. That the proof there applies to integer matrices, and they could be Laplacian, signless Laplacian, adjacency matrix, or some other mixture of that type, so long as the entries are integers. And so the theorem is I proved is suppose I have a periodic subset state, and I'm using I think that's a badly drawn L. Let me fix it, and you have a chance of understanding what I'm doing. I'm running out of letters here. And let L be its eigenvalue support. Okay. Now the eigenvalue support, since we're not dealing, is defined to consist of pairs theta R, theta S, such that ER, D, ES is not zero. Okay. Now, there's a simpler thing when you're dealing with pure states, but we're not dealing with pure states, or not dealing with just with pure states. And so we have this. This is the condition. Now the point I want to make is that the field automorphisms will if I've got to be a bit careful, I may need my densities to be, well, my densities are rational anyway. So any field automorphism is going to fix D, and it's going to map E sub R and E sub S to other idempotents. We did this in the previous lecture. What is going on here? Stupid pen. Let's just leave it. So the point is that if ERDES, if these two things belong to our, if this pair belongs to our eigenvalue support, and then ERDES is 0, and more generally ER alpha DS is not 0. So the set of pairs in the eigenvalue support is closed under field automorphisms. Let me erase that. Okay. Now that doesn't mean anything to you right now. That it will come up at a later point. Okay. So the theorem is that in this situation, and so when I talk about the eigenvalues involved in the eigenvalue supports, I'm thinking of the theta r's and theta s's, not the pairs. Okay. Now the claim is then that if we have a periodic subset state, then either the eigenvalues are all integers, or there's a positive square for integer delta, an integer A, and integers B0 through BD, such that each eigenvalue in the eigenvalue support has this form. Now, the point here is that A is the same in each case. Okay, so the only thing that's changing is the beta R's. Now, I have no objection to you taking alpha and beta R's to be even. So then you get something in the form, alpha plus beta R root delta. And in a certain sense, the second case contains the first, because there's nothing stopping you choosing delta equal to 1. Okay, but in a sense, so this is the worst that can happen in terms of the eigenvalues. The other thing, and this is an open question, is we do not have an example of perfect state transfer where A is not equal to 0, which is hugely annoying. It would make it, at least make the derivations significantly easier. You wouldn't be fussing around with things like this. But that we don't have an example of perfect state transfer where A is not 0. We do have examples of periodic states, of periodic vertices where A is not 0. Okay, but we do not have any examples of perfect state transfer where A is not 0. So I won't put that on the assignments. So, okay, so I want to prove this result. Now, I'm going to assume that the ratio condition holds. So theta R minus theta S over theta K minus theta L is rational for any provided RS and KL, or theta R, theta S, and theta K, theta L belong to the eigenvalue support, and theta K is not equal to theta L. So that's this, in other words. Now, the first comment is if you have, I'm not quite sure, I need to separate this out, probably I don't, but if I have two integer eigenvalues, and then I look at the ratio condition, and that tells me that theta R minus theta S is rational for all Q. So theta R minus theta S is in difference is rational, and actually there's probably worth making a Y on that. So all eigenvalues are integers. That's probably a good exercise. It's not too, I don't know but I actually need it, which is why I'm fussing. I don't think it is. We'll see if it affects the argument as we go through. So I'm going to assume now that at most one eigenvalue is an integer. And what we're going to show is that the square difference of theta and theta 1 is an integer. Now, there's no particular theta and theta 1 can be any pair that's in the eigenvalue support, but there's no need to make the indices more complicated. So this is what we're trying to do. We're trying to prove that this square is an integer. Now, of course, then theta 0 minus theta 1 is this integer multiple of the square root, and so we're getting close to what we want. Now, in particular, the ratio condition implies that for each pair of eigenvalues, theta R and theta S in the eigenvalue support, there's a non-zero rational number, A sub RS, such that this is true. That's just restating the ratio condition. And so now what I'm going to do is I'm going to take the product of all the pairs, theta R minus theta S, where theta R and theta S are in that pair, theta R and theta S is in the eigenvalue support. So I do that and I get this product on the left. Okay. So I'm going to have a theta r minus theta s and a theta s minus theta r, but that's okay. Just leave it. And so on the right-hand side, I'm going to get a power of theta 1 minus theta 0. And I think the exponent is d squared minus d. It's either d squared minus d or d plus 1 squared minus d plus 1, but I think d squared minus d is right. And I'll let you worry about that. So we have this, and then we have the product of these coefficients. Now, this is rational because it's the product of rational numbers. What about this? Well, this is where the field theory comes in. What I claim is that any field automorphism commutes these pairs amongst themselves. So you're looking at the pairs theta r, theta s, such that er, d, es is not 0. Okay, since d is rational, that set of pairs is closed under those field automorphisms. And the non-trivial result we need is that if you have an element of your where we're looking in the splitting field, the field of the rational is generated by the eigenvalues of A. And so any automorphism in the splitting field, or any element of the splitting field which is fixed by all field automorphisms must be rational. So it's the non-trivial number theory hiding in there. Okay, so some Galois theory. And so that means that the left-hand side is rational. And so that means, therefore, this is rational. So this power of D is rational. Now, the other thing to notice is, well, theta 1 minus theta 0 is an algebraic integer. And algebraic integers are closed by multiplication. So this is an algebraic integer. And it's rational. So it's an integer. So we're using non-trivial number theory at 2 different points. Okay, we're using the fact that because we show that this is rational, and then deduce must be an integer. Okay, and so therefore we get that theta 1 minus theta 0 to the exponent is rational. And so in particular, as I say, we get that this different power is an integer. Now we take m to be the least positive integer such that theta 1 minus theta 0 to the m is in z. And so theta 1 minus theta m has m distinct conjugates. The ratio of any 2 is an nth root of unity. Okay, now the only nth roots of unity that are real are roots of x squared minus 1. Well, I shouldn't say that, but the point is that my point is that second point is that we know that theta 1 minus theta 0 is real. And we know that the polynomial t to the m minus 1 has at most 2 real roots. And so therefore we conclude that there are only 2 conjugates of theta. Okay, and so we conclude then that that m is most 2. Okay, so now, okay, so we've done most of the work at this point. Okay, the rest of it is just a matter of tidying up. I wrote down a reformulation of the ratio condition with the ARS, and this is just taking that equation and squaring it. Now the point now is this is an integer, and this again shows that this is rational, and since an algebraic integer is therefore an integer. Or I could, that's the simplest way of doing it. So that means that any difference squared is an algebraic integer, and is any difference squared is an integer. And the argument we've used before shows that, well, it follows then that if you look at the difference theta r minus theta 0, that's an integer multiple of square root delta, the sum square free integer delta. And you don't really need to assume that delta is square free, you just get sucked into the MR anyway. This then tells you that you can write the eigenvalues as theta 0 plus integer multiple of root delta. And if you sum this equation over the possible theta r's, you get the sum of theta r's is equal to m times theta 0, there are m eigenvalues, plus square root delta times the sum of the MRs. And now this is an integer. It's the sum of the sum of the zeros, and this is rational. And so your conclusion becomes that theta r is in the extension of the rational Scott by adding square root of delta. Okay. So there are, as I said, there are a number of parts to this, but and we're using some non-trivial results in number theory, but I tend to view that as a plus. It's nice to see these things being put to work. Okay, so the conclusion is that if we have, we're using the fact that the Hamiltonian is an integer matrix and that the density matrix is rational. Okay. Now, by and large, the only irrational density matrices that this is come up will be something. Well, for density matrices, in fact, it's. I don't know if I can recall an example where the physicists were using with an irrational density matrix. I was going to say, what about the normalizing the all-ones vector? But that's not the density matrix. The density matrix is 1 over n times j, which is rational. So it's there's no pressing reason to worry about the more general case at this point, and this is certainly general enough. Any questions? Now, there are a number of consequences of this result. And I'm going to start talking about the most important one. And so we can view this as a corollary. And so if we fix two integers, k and s, k is going to be the maximum valency of our graph. Okay, so then I claim there's only finitely many connected graphs with maximum valency k. At which actually which have, let me just well, with a periodic subset of size s. So there are two parameters k and s. Okay, now the only values of s that I care about for the purposes of this argument really at the moment are s equals 1 and s equals 2. Because the s equals 2 is I think a new result as of last night. So we got these two parameters. We've got the a subset state corresponding to a subset of size s. And the way to think about this is this subset's not going to be too big. And so for the immediate applications, 1 and 2 are enough to make it interesting. Okay. Now, if s is equal to 1, we're just proving there's only finite many graphs with perfect state transfer from one vertex to another. And there's finitely many connected graphs with maximum valency k and perfect state transfer from one vertex to another. Okay, for s equals 2, we're proving that there's only finite many graphs with that show something called fractional revival, which is a generalization of perfect state transfer, which I'll be discussing later on. So let's go to the proof. We have a periodic subset of size little s, and I was actually, excuse me. Oh, blast. Yeah, well, I need, I'm referring to the covering radius of the subset. So this is the maximum distance, I'll call it delta, such that any vertex of the graph is within delta, some vertex in S. Another way of thinking about it is that each vertex in a graph, you've got a ball. You can define a ball of radius r. All the vertices do distance to most r from that vertex. And so the covering radius is the least r, such that the balls of radius r about the vertices in S cover all the vertices of the graph. For a single vertex, the graph theorist will call this the eccentricity. And I used that terminology when I talked about it earlier, but I actually prefer the covering radius terminology. And in this case, it makes more sense. So the covering radius terminology is coming from coding theory, which is appropriate. So this is the, I'll just flag a note. Yeah. So this is the maximum distance of a vertex in S. Now the point is that if S is equal to 2 and the covering radius is 10, the graph can't be too big. or especially if I bounded the valency and bound the covering radius, I essentially bounded the diameter. Okay, and if I have a graph with bounded valency and bounded diameter, then it's got, it's an unbounded number of vertices. So it's going to be a combination of things. But in any case, that's getting ahead of myself. So I'm going to take D diagonal 0, 1 with DA. So this is a subset state, not properly scaled. Now, the first, and this part of the proof is very similar to what we saw before with the diameter versus number of distinct eigenvalues bound. And okay, the next claim is that these matrices are linearly independent. Now, D is diagonal 0, 1. And so it's the same proof as before. As you multiply by larger powers of A, you cover more and more vertices. And probably this should be A plus I to the not just ADR. So that's not going to matter. Now, so they're linearly independent, and they lie in the span of this set. Okay, so this is a set of span of matrices, but that's all right. Now, the point to notice, if ERDES is equal to 0, then ED is not 0. And the key thing here is that ERDES is equal to ERDES. And this is equal to yes, D transpose. Okay, so now if ERD is 0, then ERDES is certainly 0. Okay, so we can okay, so now if so what I'm saying is that if this is 0, then ERD is not 0, and similarly ERS is not 0. And this tells me that, setting up my line, tells me that each eigenvalue in the eigenvalue support lies in the set of eigenvalues theta r such that ERD is not equal to 0. So this is just a set of eigenvalues, not a set of pairs. And so it follows that if nu denotes the number of eigenvalues theta r such that ERD is not 0, we have that the covering radius plus 1 is at most nu. Okay, and so we have a bound on the covering radius in terms of the number of eigenvalues which that is true. And so now we get to all eigenvalues of the graph, since the valency is bounded by k, all eigenvalues lie in the interval k to minus k. And since the difference between distinct eigenvalues, the eigenvalue supports at least 1, the size of the eigenvalue support is at most 2k plus 1. Okay, this is okay. And so the vertex of the graph is covered by the S balls of radius r about the vertices in S, and so consequently the number of vertices is bounded by a function of k and S. And so that gives us a general statement about when subset states are periodic. Now, you could try and push it a bit. If we have a diagonal matrix, quasi-semi-definite matrix D, then every quasi-semi-definite matrix has a unique quasi-semi-definite square root. And so instead of saying ERD is not equal to 0, I could be worrying about ERD to the 1/2 not equal to 0. The problem comes is I don't know what the entries of D to the 1/2 are, and they're likely not rational. And so when at some point I'm using the fact that I use the fact that the entries of D are rational. It's possible that this could be extended to other states, but you need a restriction, and then you need to come up with a restriction which gives you a class of states which are of some interest. Okay, so it's easy. I mean, a state's just a density matrix, quasi-semi-definite trace 1. You can write down any number of them. Okay, if you're going to work with them, you'd like them to be interesting. Okay, and so related to things which might come up in practice, and so subset states seem a natural point. And there's also a connection to this problems with fractional revival, which I'll be discussing later. And that's it for today.